Okay, ladies and gentlemen, welcome back to the Design on Cloud Pavilion, which has been sponsored by Google Cloud and Microsoft. We have our next presenter is a professor of engineering and computer engineering at NYU, and his name is Ramesh Kharif. Please give him a warm welcome. Thank you.
Thank you. I know you're tired, so you've been sitting. I hope you relax a little bit. I am Kari Ramesh, a professor of electrical and computer engineering at NYU. I co-direct the Center for Cybersecurity at NYU. And whoever had me here, thanks for having me here. So here is the cybersecurity team at NYU. This is most of the team. We at CCS look at cybersecurity from multiple angles. We see it as a IT, IS, and computer science problem, which is what most of us are used to looking at it. But besides, we also see it as a chip level issue, a firmware level issue, embedded systems level issue, software networks, and all the way up the stack. Less important to you, but more equally important, is we see it as a human psychology problem, social engineering. Most of us have fallen for that. We see it as a human rights problem in countries that do not have sometimes access to stuff. Stuff gets disconnected. We see it if you're a business, if you're in business of selling stuff. We see it as a risk management issue and as an economic risk issue. So we look at all of those aspects, but I will not talk about any of those aspects today. What I will focus on is hardware cybersecurity. We have a team of 5 or 6 faculty in hardware cybersecurity. We have a booth upstairs, 2354, 45 switched a little bit. And we have 4 of us here, Oscar at the bottom, Siddharth Garg and Mihalis Maniatokos. We are all from NYU, and we focus on hardware cybersecurity. So the cybersecurity research at NYU is a world or a global scale effort. We see CCS has a strong presence in the Middle East. For those of you who do not know, we have NYU has a campus in NYU in Abu Dhabi. It's our beachhead there. It helps us sometimes understand important cybersecurity threats before they come to our shore. Depends where I'm talking. And offers a cultural perspective of cybersecurity threats. We span multiple schools. As you see, engineering is the basis. But within engineering, we have computer science, electrical engineering, and mechanical engineering. I won't talk about some of those things. And we have folks from law, Steinhardt, and public policy, business school, and so on and so forth. So that's what we do. So that's a small backdrop on the Center for Cybersecurity. So let's get back to the problem at hand. Over the years, electronic hardware has become the core root of trust for any system, from buildings to your pets and everything in between. However, as you may have realized, and you're part of this, there's been a globalization that's been happening, and this globalization of the IC and semiconductor supply chain over the last couple of decades has introduced numerous security issues. And because of this basic assumption that the core root of trust is trustworthy is no longer true. The systems that use these core roots of trust are no longer trustworthy henceforth. So what I'll try to do in this presentation, I won't give you any results or anything. I'll try to paint my vision of hardware cybersecurity, or the emerging era of secure computer engineering, whatever you call, and the implications on how integrated circuits and systems will be and should be designed and managed and so on. So let's see. I'm sure, so this is an outline of my talk. I have one more bullet that was missing on the slide, but that's okay. So this is the typical design flow. To understand the security problems in hardware, maybe let's look into this typical IC and system design flow. An IC company typically has an in-house design team, most of you are aware of that designs some of the components. However, this team cannot and sometimes does not design all of the components. They procure them from outside vendors, right? These are intellectual property cores. The sellers are IP vendors, and putting them together is IP integration, right? So they buy some components from other companies, and companies that and then the design company inside to it has a integration team that puts together all these components, and the design is then synthesized into an RTL netlist, and its netlist is basically a collection of components and their interconnections. I sometimes I give this to a more general audience, and usually we don't have IC designers in my audience. So you will see my explanations as being extremely basic, and I'll leave it at that. So after this integration of these components, you go through what's called logic synthesis, which takes this register, which results in what's called a gate level netlist, collection of gates and wires that connects these gates, right? Then followed by physical synthesis, it creates a layout, collection of masks used to guide fabrication steps in the foundry. The mask deck is sent to a foundry where ICs are printed on semiconductor wafers, and this process is typically imperfect. So then these wafers are tested for manufacture time defects. Good ones are sorted out and packaged and assembled into large scale systems, and so on and so forth. So that's a typical design flow that most of you are aware of. So circa 1990, for those of you who were in this industry at that point in time, long time design process was vertically integrated. Many of those companies no longer exist. Design, manufacture, test, packaging, and assembly of ICs were all done in-house by a single company under one roof. That's important, right? It's centralized. The products were sold worldwide, and the IC technology, of course, at that point in time was quite complicated, but it was tens of hundreds of microns. So let us see how this is done by considering Apple as an example. So it has design houses in Europe, China, and India. It manufactures its chips in, any guess? South Korea, sometimes it could be in Taiwan too. And testing and packaging are typically done in Taiwan. And finally, the system is assembled in the Silicon Valley, and the Apple products, of course, are sold everywhere, and all of us have possibly one product in our pocket or on our arm or wherever it is. So if you look at this, all the IC and system design steps are geographically distributed, right? And this is the closest I'll come to the cloud-based stuff. But anyway, almost all the IC and design steps are performed offshore. Depends on which country you are in. Everything else is done offshore, right? Where you are. Several contributors to this trend, or several drivers are contributed to this. One, printing high-end semiconductor technology, tens of nanometers, is very expensive, right? And you have to get these foundries updated every so on, roughly $5 billion every time you do that. Driver two, low cost of technically skilled engineers or labor in Asia. Number three that we cannot compete with is subsidies, right? Government subsidies in Asia and to build foundries and so on and so forth. So these were the drivers for the distribution of the globalization of the supply chain, and comes with all of this are the problems that I'll talk about. So let me see, where am I? Okay, so that's done. So globalization has resulted in several problems. I'll talk about a couple of them. One is what's called the hardware Trojans. Here an attacker can make malicious modifications to the design. And the objective of inserting a Trojan or a malicious modification could be to control, to modify, or to disable the system, or to leak sensitive information from the end system. At least two scenarios. Scenario one is a rogue in an IP vendor company has a backdoor into the IP itself. In the second case, the foundry can insert a Trojan, right? So you can see it happening both places. And there are other places where things can happen too. And the question then is this a real problem? And yes, hardware Trojans are real. Example, in 2008, Syrian radars were supposedly maliciously turned off when Israeli jets flew into the Syrian airspace. And these are anecdotal, by the way. It's claimed that a hardware Trojan disabled the radar so that the aircraft could go undetected. So that's one class of attacks. The second one is what's called reverse engineering. Here an attacker tries to identify the device technology used in an IC or tries to recover the functionality that's embedded in the design. So reverse engineering potentially facilitates variety of additional capabilities, Trojan insertion and piracy, for example. Once I figure out what the chip does, I can probably make it better, right? Example, the SoC integration house or the foundry or the user, any of these could be potentially problematic sources, right? Places where things could happen. So this is the typical process. The reverse engineer takes an IC, depackages it, delayers it, takes images of these individual layers, annotates them, analyzes these images, and potentially extracts the design. By the way, there's a company that does this. It's called ChipWorks that performs reverse engineering for competitive IP analysis purposes and so on. But they do it to detect piracy, but you can also do it to create privacy. Impacts include IP theft, IP piracy, and so on and so forth. So let me see if I can convince you that hardware cybersecurity is indeed important. To understand this impact of hardware-based attacks, let's consider the different layers in any modern information processing system. At the bottom, you see hardware. If you look at it, until now, attacks have been common at the user, application, and OS layers. Examples include social engineering at the user level, malware at the application layer, rootkits in the OS, and so on. Hardware level attacks are beginning to happen, and I've talked about a few of those now. Now let's look at their relative impacts, and this is my claim. Hardware-based attacks, I think, do not need user intervention. Once they are introduced, they live in there. If you have some software-based attacks, you can at least patch them. So at the very least, the impact could be of the order of the same order of magnitude as OS level attacks maybe. It could be even worse, but many of you got aware of I used to make up these, or rather it took me some extra time to convince you of the importance of this, but after Spectre and Meltdown, some of these slides are no longer important, okay? So let me talk about 3 design for trust techniques. At a very high level, I'll talk about one at the standard cell level, the second is at the manufacturing level, and the third one is at the high level, which is what the title of this presentation was. So to make it simple to explain the 3 kinds of defenses against some of these attacks, let me give this particular table. To guide through the defenses, this is a table I want to use. The foundry could be trusted or untrusted, and the user can be trusted or untrusted. There are additional places that things can go wrong. Suddenly the table becomes multidimensional. So I'm just making it simple and say, let's have only the user and the foundry, right? So let me use this table to situate the defenses. So we talked about several of these techniques. Trojans, I haven't talked about counterfeits. I briefly alluded to reverse engineering, piracy, and overbuilding. So I'll talk about 3 techniques. One is, we call this design for trust techniques, by the way. Going to Icy Camouflaging. It's an interesting technology, provides a layer of defense. And the second one is split manufacturing. Again, adds an additional layer of defense. And the third and final one is algorithm level obfuscation. Okay, so that's the high level. So these are the 3 techniques. I'll talk briefly about each of them. So let's look at Icy Camouflaging. Here, the designer trusts the foundry, but does not trust the user. The key message is, for every defense, you need to have a clear threat model. That's the other message you need to get out of it. So this is a layout level technique used to thwart reverse engineering attacks, and typically reverse engineering is done by taking images layer by layer, peeling off the layers and annotating them, stitching them together. I talked about that. So, and ICs are designed using a library, typically consisting of pre-designed standard cells like NAND, NOR, buffers, D flip-flops, and so on and so forth. So, if you look at these things, standard cells, for those who are well versed in the art, that is physical designers or standard cell designers, by looking at those structures, you immediately can figure out the functionality. There is a correlation between the structure and the function, right? So if a reverse engineer encounters the structure on the left, he figures out it's a NAND gate. And if he encounters something that looks like the one on the right, he figures out that's a NOR gate. And that's how they figure out, reverse engineer the structure. So camouflaging does something slightly different. If you look at the right hand side, do you see any difference between the two cells? The answer is, I just made a cut and paste of them. At the top level, they are not different, right? So camo cells are designed to look alike, independent of their functionality. The functionality is different, but at some level, at the top levels, they are actually looking identical. So if you take an image, you cannot say if it's a NAND or an OR gate, right? Imagine you have standard cells like this, right? All of a sudden, you can thwart that particular attack. But what's the catch? That doesn't implement a NAND or a NOR, right? So at some point, there have to be the appropriate connections to make it implement a NAND or a NOR. So let's see what happens. So this is how you do that. So although at the top they look identical, as you go deeper into the layers, you might have differences that are related to the functionality, right? So one way to construct the camo cells is what's called using dummy contacts. At the top level, you see contacts, but they don't go all the way through, right? So if you look at on the left-hand side, you have a metal 1 to poly wire the full connection, but on the right-hand side, you don't have that. And when you take images from the top, you are forcing the attacker to peel off more layers. As they peel off more layers, more errors creep in and so on, right? So you make their task that much more difficult. The next question is, this is the design flow. Instead of using standard cells, you also use camo cells. Of course, camo cells are expensive, so you use some of those camo cells, and the rest of them are regular cells, and you combine them, and suddenly, what does an attacker do? You have the chip, and he goes back in that fashion, right? So he's gone all the way up, and I have a single camo cell there. He doesn't know whether it's a NAND or an OR gate, right? Because at the top layer, they look identical. Now imagine that you have many of these in the design. Imagine you have 1,000 of these. Now he has to guess each of them correctly. So the combinations are 2 to the 1,000. So all of a sudden, you prevented that reverse engineering attack. This is a very best case scenario, but there are other ways this can be thwarted. The cost is these camo cells are expensive, so you have problems. So you cannot make everything, you can't use camo cells all over and so on. And so there are design trade-offs and so on. So that's the first technique. Who uses them? By the way, TSMC supports this technology. SMI is the company that has come up with a variety of camo cells. That's their proprietary technology. Lots of chips actually support camouflaging. Typically, in fact, set-top boxes were the first people. It's not DoD, it's the set-top boxes that were worried about people who don't pay their bills and get the IDs from the neighbor and so on. So that was where the most advanced hardware security was going on a long time ago. So the next technology is what we call split manufacturing. Here you don't trust the foundry and you trust the users, right? So that's the use case there. So again, for those of you sitting here, probably you understand some of this jargon. So what we are suggesting here is to use, so you have what are called, let's talk about the front end of line layers, right? These are the pitches of the transistors and lower metal layers. That's one part. And suppose you want to manufacture them. Since these are subsidized elsewhere, you can use the advanced foundries outside. Then you have BEOL layers, back-end, which is the fat metal lines and so on. They don't need an advanced foundry. You can use a low-end foundry. These can last longer, right? So you could use that. So the question in split manufacturing, or the proposition of split manufacturing is, can we outsource the FEOL to the advanced foundries, get them back, and somehow put the BEOL layers on top? There are two ways you can do that. So you want to, of course, here from a cost perspective, you want to get the benefits of high-end foundries by using the costs of low-end foundries, and while at the same time being secure. So that's the idea behind split manufacturing. This is a typical design flow. You have your GDS2 file. You split the BEOL layers and FEOL layers. Where you split is an important question, and we won't talk about it. But depending on where you split, you have security benefits, redesign costs, so on and so forth. And then you can slap them together in a trusted source, or you grow the BEOL after you get the FEOL. There's lots of problems in shipping wafers and so on. But there's a project that is ongoing that has actually figured out how to understand the problems and make sure that these things can be done. There's a DARPA project that's ongoing on this. So this is a different way of providing security, right? So you don't have to give away your secrets to the untrusted, potentially untrustworthy, outsourced foundries, right? Without, this is a DoD-centric problem. Yeah. Then we come to the third part of the talk, which is high-level synthesis for obfuscation. So it's not at the gate level or at the foundry level that you want to incorporate security. You want to have it systematically throughout the entire design flow, right? It should not be an afterthought. It should be a first-class design metric, side-by-side power, performance, reliability, so on and so forth, right? So I talked about gate layout level. We have done stuff at the gate level. So let's look at RT and architecture level, right? And if you talk about RT and architecture, one of the most popular technologies these days is the electronic system level or high level synthesis, whatever you call it. It used to be high level synthesis when I was doing my PhD sometime back, but it came back as ESL now, okay? Anyway, the benefits are numerous. Enables design at higher abstraction levels, C, C++, Java, or whatever language you have. Numerous semiconductor companies use ESL tools. Popular applications where domains are communication, signal processing, computation, cryptos, data dominated designs anyway, mostly. Control is also happening, but mostly data dominated. And then it's seen more as a productivity tool, right? So now that you have enough real estate on the chips, they don't know what to do, so they said let's increase productivity by starting at higher levels and so on. High level synthesis essentially raises abstraction from RTL to C, C++, or whatever system level. Allows early design exploration. You can explore alternate designs. Applications are image processing, compression, and so on. There have been lots of example chips that have been built out. Here, Tegra X1 was designed using Catapult HLS, I was told. NVIDIA 4K was designed with C-based HLS. Qualcomm designed parts of its Snapdragon with Catapult, so on and so forth. Vivado HLS is part of the Xilinx design flow. Intel acquired Quartus design flow from Altera, and so on and so forth. So lots of fun stuff. So high-level synthesis design flow is something like this. You start with a high-level specification, translate an intermediate representation called the control data flow graph, and then you do a couple of steps. One is the scheduling, which is mapping operations to cycles, and binding, which is mapping operations to operators. And you get something like the top, middle thing, scheduled and bound, and then that implies, directly determines this controller on the right, all the way to the right-hand side. It's a straight line, straightforward controller. And then you get the data path, which is data, and the tiny controller somewhere in there. So that's a design flow, right? So many of you know this. So now let me take this as my context and look at security benefits that these things offer. So what I claim, or this is an emerging piece of research that we've been doing over the last year or so, our claim is it's easy to incorporate security constraints at this high level, because as a designer, you know what's valuable, and at higher levels, it's easier to know what's valuable. So if you look at it, so I put an analogy between hardware and software. You start with layout, gate, RTL, and algorithmic level, and the equivalent on the software side is the binary bit blobs and assembly and so on, and programming level, programmer language level, and so on. So if you look at that, as you go down from the high levels to the lower levels, there's a lot of semantic information that's lost. The more semantic information you have, the better decisions you might be able to make for whatever it is, including for security. That's our claim. So ease of securing goes up as you go from the layout levels to the algorithmic level, because you have more information, more semantically meaningful information to play with and to operate on, right? So, so that's our claim. So if you have something, semantic information at this level, why not use it? That's our question. So now you do not need a security engineer to do all of these security relevant, incorporate security relevant defenses. You can also have regular designers who know what's important for, as part of their design, use these high level information and make appropriate decisions. So before I go into the before I go into the defense, I want to reiterate what the threat model is. Here I have an untrusted foundry. That's my threat model. So I have a chip, I'm sending it to the foundry, I don't want them to recover my IP, right? How do I prevent that? So these are some of the capabilities, and again, I will keep it reasonably high level, and I won't give you any more details than if you want, we have a paper day after tomorrow, I think. So if you want a DAC. So that's what I have here. So this is what it is. I have an obfuscated netlist potentially somehow. I'll show you how to do that. Then I have a key that functionalizes this netlist. The claim is, absent the key, I force you to explore all the possible combinations. So 2 to the k netlist, which you would rather go and hack somebody else's chip rather than mine. That's the idea here. And once the chip comes back, I functionalize it because I know the key. Okay? So this is the threat model, and this is what I want to accomplish. So the question then is, how do I obfuscate? I can obfuscate at multiple levels. We have done it at multiple levels, including at the standard cell layer level, which is the camo, right? And so on. But let's look at the algorithmic level. Right? Here is the simple function you have, right? See, that we easily understand. So lots of obfuscations you can do. You can obfuscate the control flow, it's semantically meaningful. You can obfuscate the constants, proprietary constants for your DSP filters, whatever you have designed, because that's the important, the secret sauce that makes your DSP work as well as it does. Dependencies and the types of operations. These are the 4 things that you can obfuscate, right? So control flow obfuscation essentially describes the evolution of the algorithm. And when you do obfuscation, it looks obvious, but you got to be very careful because it's always easy to eliminate bad obfuscations, right? So you guess a key and see what control flow gives. It says just doesn't make sense. So when you create these obfuscations, you want to make sure that the alternates are equally plausible, right? So that's the challenge here. So anyway, I won't. So given the key, you get the right flow. Otherwise, you might sometimes be okay, other times not be okay. And if you have multiple of those, suddenly it's a mess. So you can see that. You can obfuscate operations. So the thick lines are the normal operations. The dotted lines are the dummy, fake, decoy operations, whatever you call them. And once you insert a few of those, suddenly you create doubts or you obfuscate the functionality. You can recover it by figuring out the right key a bit to select the right output, right? So that's a functional operation obfuscation. Constant obfuscation, you have lots of constants, lots of useful constants in your chips, in your algorithms, in your implementations. When you synthesize everything and you go to the layout level and so on, all those constants disappear in some sense, right? They are hardwired and so on. But at the high level, you have that information remaining, and you'll say, this is useful, this is not useful, this can be easily figured out, so let me focus on these. And you can do all of those things, and all of a sudden, they provide you a rich material from which you can obfuscate or create your key or figure out what the keys are, right? So a very simple example here, how do you obfuscate them? You take these constants and replace them with e-fuses, for example, right? And then when it comes back, you blow those fuses to the right values, and suddenly it's functional. That's one way of doing it. You can do it other ways where you have registers, you shift in the right values, scan in right values, and so on. So that's the other thing you can do. So you can obfuscate constants. And the benefits, the security benefits, all of those are in the paper. I'm not, as I said, I'm not giving you the results. We have a functional tool. Anyway, dependencies. You can also add some dummy wires here and there and create more confusion. So to summarize, I pointed out four places at the high level where you can obfuscate and create confusion and insert keys into the algorithm that you're implementing. And control flow, operators, dependencies, and constants. Okay? So that's a typical design flow. And if you look at this design flow, high-level synthesis is a good, obvious place where we all can think we can incorporate these security constraints. But the problem, there is a slight problem there, because each high-level synthesis tool is proprietary. Then you have to go and incorporate this into every synthesis tool. So as we were working on a project, we realized that, and of course that was the focus of our paper that we're presenting today. As we were doing this, we realized that what if we can, what is the information that gets retained, the semantically meaningful information that's still remaining in the obfuscated RTL? A lot of information is remaining. The constants are still there. You haven't done the logic synthesis, so the gate level netlists I haven't formed. So at the RT level, you still have a lot of semantically meaningful information, and that's independent of the tool. It doesn't matter what high-level synthesis tool you use. At the obfuscated RTL, RTL is quite independent, right? You have a everybody generates the same RTL almost, and then you can play there too. So we have looked at that aspect of it, and it's compatible with most tools. And you don't have to buy into anybody's tools. And in fact, so I'll leave it at that because we have other things to say. So I hope I convinced you that that hardware level defenses, attacks are pernicious, high impact from an attacker's perspective. They can cause lots of damage, even if it was unintentional. In the case of meltdown and Spectre, if you want it to be deliberate, backdoors are quite easy for those of you who follow these things. Countries, standards, organizations are also infiltrated, at which point cryptographic algorithms and the standards are also infiltrated. Look at this, Google, some of these things. So it's easy once you put them in hardware, difficult to patch, right? So that's the problem. And so design for security is important, and you can do design for security at all layers. At the highest level, the designer himself can participate in this effort, where he can use semantically meaningful, sensible information. And then you can go as the layout level and the split manufacturer, the foundries at the lower layer, also bring in some more defenses. And all in all, you have what's called the defense in depth approach. And that's all I have. I don't know how much time I took up. If you have questions, I'm ready to answer. How did I do on my time? And if you have, if you need more, yeah, perfect. More details. Booth number 2345. No, that's too good to be true, right? 2354. Yeah, we have a lot more than what I talked here is there, and I have about 15 of our PhD students hanging around, 5 of our professors there, and I hang around sometimes. Thank you.